Hello everyone, it's April the 5th. Today I have been working on some reinforcement learning stuff and I got a bit stuck. So let's do this for a change of mind. Maybe it'll help me back then. And I also hurt my neck, but that's fine. Alright, let's take a look. Anything trapping rainwater? Yeah, it's always a difficult question. Alright, let's take a look. What do we have today? Global and local inversions. Look to be a medium question immediately. We have some permutation A of where n is the length of A. The number of global inversions is the number of I smaller than j with this and AI larger than AJ. The number of local inversions is the number of I with this and AI larger than AI plus 1. This is the global inversion, which is the number of I smaller than j. That, okay. The number of local inversions. Oh, okay, that's local. Got it. Well, I actually shouldn't I be smaller than, yeah, I small, where the I and j is 0, so I should be n minus 1. Otherwise, I plus 1 will explode. Anyway, return true if and only if the number of global inversions is equal to the number of local inversions. Okay, so what we have is this. There's one global inversion, which is this. Alright, that's the global inversion, the number of ij, such that I smaller than j with ai larger than aj. Yeah, inversion. No, what are you doing? ai larger than aj. ai is not larger than aj. This one. This one, ai larger than aj. That's a global and it's also a local because I plus 1. This one we have, this is a local. This is a global, but we have two global and one local, okay? A will be a permutation of this. A will have a length in range this. The time for this has been reduced. The time level has been reduced. You have to be smarter. Okay, so global, local is easy to determine because it's I and I plus 1. So we can just run a sliding window, right? Two at a time. Two at a time can count the number of local. Now, if you're a local inversion, you're guaranteed to be a global inversion. So the task is essentially to find the number of global inversion that is not a local inversion. If there exists, then it's going to be false, right? So the question is just how many global inversion that is not a local inversion, which means I can see how the on squared algorithm goes. So we can go this, right? Every time we're going to start from 2. Right, because we don't do right next, we can do n and n plus 2, right? N and n plus 2, and we can move sliding window, and then n plus 3 sliding window, n plus 4 sliding window, and then just to see if any of them match. And that is an O(n) squared solution. Let's code it. Let's make sure that we are thinking about it right. And this is going to time out. I know it because of this sentence. That means it's going to time out. However, it's always good to write a solution that you know is accurate. It's just because it times out. This will give us some, we can also use that as a way to create test cases. So this is, again, I want to emphasize that this is not the correct answer in terms of doing it within the time limit. We use this just to gauge if our understanding is correct. So we have an A. So what we do is we're gonna do for what? So the largest will be, so it's 0 plus 0, 1, 2 plus 2. So I'm going to be for D in range. So I'm going to do from 3, right? Well. There are cases, right? If A is 1, then that's going to be true, right? Let's try it because both are 0. Let's try. So, oh, nice. This could be true because both are bad. Yeah, that's true. And if it's 2, then the result is also true because both are 1 or both are 0. So we don't have to consider these situations. Basically, we say n equals len A, and if n is smaller than or equal to 2, we return true, right? Because if the other way around, it's also going to be true. Yep, that is correct. So if it's true now, we can say if range is 3, so we can do plus 2, right, to n minus 1. Plus 2. Plus 2. We can do plus 2. So actually it's 2n, right? So we can do n if it's 3, we can do plus 2. Yeah. So what we're gonna do is just check if it's good. I'm gonna say if for D in this range, and then for I equals 0, right? I equals 0, and say while I plus D is smaller than n, then we do if what? If I is larger than I plus D, we return false, right? We return false because that is a 1. It's not inside. That's the 1. That's a global inversion. That's not a local inversion, right? And if not, I plus equal 1. I'm going to keep going. I think we can do a for loop here instead of doing this. I can just say for I in range n minus d, right? Yeah, I can do to n minus d. And then we say if this, then return false. And then after all done, we'll have to until this all done, then we'll return true. Right? I think that is, I'm not so sure if it's correct, but we can give it a shot. Let's run like 2, 3, 4. No, not 4. 2. 2. Okay. Just take a look. True. Pretty sure it should be correct. 2, 3, 2, 0. Right? That's the test case here. It should be false. Yeah. It should be timeout. Expected to timeout. Looks promising. Yep. Timeout. So this is correct. Yeah. So our understanding is correct. So this is a TLE, but don't worry. This is expected. Okay. And then we can use this to write test cases. Right? We can write test cases. So we're gonna say solution TLE. Yeah, I'm gonna do solution. So I'm gonna say TLE equals solution TLE, and then we're gonna do another solution. That's the actual one. Now we're gonna do, right? That's an actual solution. And now we're gonna from iter tools import permutations, right? And then we're gonna say the solution. I'm gonna say base equals, let's say list range. Let's do 10. Let's do 5. 2, and then tests will equal inputs. So inputs equal permutations. Iterable will be base. I think I can just use range, right? I don't have to use a base. I just do this, the permutation. Range this, and then tests will be equal to for input, right? It's gonna be input, not input A, and the answer will be TLE dot is A, right? For A in inputs, right? You can put it up there, and then we can try. This is going to be A, and then this is what? This is and then A, okay? And we just do return true. Let's run it. See what happens. Yep, we have 120. Yep, that is correct. Answer false. Answer false. 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 It's true. Okay, that's good. That's good. So we have now a very exhaustive test on small values. Now we're gonna try to figure out a way to solve this in a smarter way. All right. So basically, how can we make this one smarter? Give us an example. I have an example. Any example. Let's say we're looking at any values. 1, 3, 4. Right? So what we can do is, like for first value, we're going to compare to the second. To the third. Actually, I can do a slightly different way, but it doesn't matter. So compare the second, the third, the fourth, right? And what we want to do is find. I only need to find one. We have to check all of them because otherwise we don't know, right? So we need to check all of them. So if the current value is the smallest, then we don't have to check because there will be no inversion. And if the current value is not the smallest, we need to know where the smallest are, right? And then that's your inversion, which means if a given value is 0, then we can skip because there will be no inversion. I mean, we're looking from current value and always look to the right. Always look to the right. Right? Always look to the right. Current value, we look to the right. So we only consider a value, we don't have to consider again. So if it's 0, then we just skip and we'll look at the next one. So any value that's not 0, right? Say we're looking at 2, and we know 2 has 0 and 1 is the smallest. So we look to its left and look to its we look to its right. Right? We'll look to its right. And if 1 is on the right, and that's the only one that's smaller. Yeah, so like we have to find a smaller on the right side, right? On the right side. How do we know that 0 is not on the right side? Like if we're given any value, well, we can put the value we have checked inside like a set. Say if all right, let's make this a little bit. So what we have is this, right? Let's try to run this. God, what are you doing? 2, 1, 3, 4. All right. So we check 0, and it's bad. And then we put 0 in our set, right? Set, we have 0. And now look at 2. So 2, we have 1 and 0. Oh, then every single one, we have to check all of them? That's bad. I mean, like for 2, we know the one smaller than 2 is 0 and 1. And we say 0 is already checked, so we only need to check 1. And we look to the right, immediately to the right, that's 1. That means there'll be nothing beyond that is smaller than 2. So 2 is, we can skip. So 2 skip, we put 2 here. And at 1, we need a 0 and a 0 in it. So 1 is skip. And we look at 3. 3, we need 0, 1, 2. And they're all considered so far, already considered. So there'll be nothing smaller than 3. So we put it here and put it here. And this one is a true. Yeah, this is a true. This is a true, right? I use this to examine. I think this is true because we cannot find a global inversion. Yeah, but how do we know at each value? We want to know if there exists a value that is smaller than this that we have not encountered yet, right? That's the question for each value. We want to see if there's a value. Basically, we want to see, what do we want to see? We want to see the value that's smaller than the current value, which has not appeared in what we have checked before. Okay, so, and what we have checked before, what we can do is, can we like put them in the data structure that we can put them in a sorted order? How can we do that? We want the front to be sorted, like to be always sorted. I mean, we cannot do that because I want to know what value that sorted. If we want to sort, every time we insert, I want to make it sorted. If we can make the front all sorted, then when we put this one in, we still don't know. Oh, then we know, right? We put this one in. We just want to know how many values are ahead of it, right? If we put 3 and the values in front of it, if that adds up to 3, then we know there's no value that's smaller than it. Otherwise, we know there is one. This seems to be... So let's say we have an array, right? And every value starts with 0, right? And when we start is like this. And we 0, then we set this to 1. Because 0 has encountered 2. When you set this to 1, now this has to be 2. But how do we know this is 2? Right? And a 1, when you set this to 2, you want to set this to 3. And then when 3 comes in, you know you have 3. Like this has 3. Because if not, every time you have the sum, right? You have the sum, and then we're encountering the same issue. Like every time you hit this, you sum the front, which sum takes on, and is on squared again. On squared again. But we want to reduce it, right? We don't want it to be on. So every time encounter a value, we want to know how many are larger than it and how many are smaller than it that have already been encountered, right? How do we do that? How do we it has to be sorted, right? It has to be sorted, but we cannot sort as we're pushing the value in. I think we might be thinking about it wrong. I'll give you, it's a permutation of this, right? It's a permutation of this. So any value we encounter, we know how many value has already been encountered. And yeah, we know how many value has already been encountered. Now the only chance that it's going to be true, right? If you look at this, a lot of them are false, right? So the only chance that it's going to be true, the only chance that it is going to be true is as we do this, every value when we encounter the one that's smaller than it is right next to it. Right, so the smaller than it is right next to it. Okay. We might find okay. So the only chance, if we want to be true, right? There are two situations that it can be true. The result will be true. One situation is at our current value, there is one next to it is smaller than it, and the number, yes, the number of values that is smaller than my current value, if it's equal to the values and the number of values are in front of me, plus 1 right next to me, that's a true situation. Or no, or oh yes, or the number of no. I'm jumping back and forth. So this is true, right? If the number smaller than me is in front of me, and we have encountered, well, that doesn't make sense, right? That doesn't make sense. So we can do like 3 4 0 1 2 0 2 1, right? If we encounter 0, well, that's a false, because no, that is 0 is the smallest, so it's always going to be true. Like 3, oh, that's a false. 3 is, we have 2 smaller than it. So okay, that's an easy way to check the first one, right? So if the first one, oh, maybe the second one, hold on. If the first one, all right, I'm back. How do we know 3 is false? Because for 3, we know for 3 there are 3. For every number there are 3. For 3 we have 3 values that's smaller than it. And in order for 3 to make it true, the only situation is either those 3 values are all on the left side, or 2 values on the left side and a 1 value is at this position. So we check. 3 is the first value, so there's nothing on its left. So nothing on its left. So that's definitely is a false. So we by looking at the first value, we already know this one's a false, right? Which means we can find the minimum value that is at the front, and it's going to be false. So that can eliminate tons of cases, right? Tons of cases. So what's the minimum? So the minimum will be if 1 is at the front, right? Then 1, 0, something, something. This is still considered true. But if it's not 1, 0, it's 1, something else, then that's a false. Now, 0 at the front, we cannot determine. We have to keep moving on. But if it's 1 at front, then we know. Now, if 2 is at the front, then no matter what you do, because we have 0 and 1, so no matter how you place it, if 2 is at the front, it's definitely false, right? So 2 at the front is false. So the only chance that's going to be true is 1 or 0. Is 1, 0. 1, 0 is true, and 0 something might be true. So these are the only 2 cases. So we can actually print it just to verify that what we think is correct. So basically, we can print. Yeah, we can just print everything, right? We print everything. So we can print this and we print A, right? We print this, we print A. Let's take a look. This is not correct. We have to return something. All right. So the true is 0 at the front, right? 0 at the front. 1 at the front, 1, 0. And that's it. Right, exactly. That's what it is. That's what it is. So now we only need to consider when 0 is at the front, right? If 0 is at the front, then what can be the situation? So I think it's the same situation. If 0 is the smallest, then we can consider 1, right? And for 1, the only thing smaller than 1 is 0. So everything else is larger than 1. So 0, 1 is... So yeah, 0, 1. We can keep consider 0, 1, and 0, 2. So if 0 is the front, 1 will pass, right? But 0, 2 will have a situation. So 0, 2, 1 will pass, but anything else will fail. Right? So in that case, we are just repeating. We're just repeating the same. We're just repeating the same thing. Right? We're just repeating the same thing. We can actually list out all the situations that will pass. So 0, 1, 2, like in order, that's going to pass. I mean, that's going to be true, right? In order, that's going to be true. And then what? Let's just do 2, 4. 0, 1, 2, 3, 4 will be a pass one. And then if it's 0, 1, it's going to be, if it's 0 at the front, and if I have 1 and 3, and then it will be 4. Okay, now consider if not 3. So 0, 1, 2. If it's 0, 1, 2, so they all pass. Now next one, if it's 4, that will pass as well, right? If it's 4, that will pass as well, because the only one that's smaller than 4, we have 3 in the front, and then 4, and we have 3 right next to it. So that will also pass. And then go one step back. So 0, 1, how about 0, 1, 3? If it's 0, 1, 3, it has to be 2, right? That's the only time and it will pass. And then rest doesn't really matter. So basically, I think basically we can just consider all the passing situations, right? So 0, 1, 3, that's passing, and that's the only situation that's going to pass. 0, 1, 4 is not going to pass because we have 2. So when we do 0, 1, 3, that's going to pass. So 0, 1, 2, we have 2 situations that can pass because so 0, 1, 2 is actually passing. We move on to the next stage. But 0, 1, 3 is only 1 situations. And 0, 1, 4 we cannot do. So now we can consider 0, 2. If it's 0, 2, we can do 0, 2, 1, that's passing, but all the others will not pass. Okay? 0, 3 will not pass. So that's it. So for 0 at the front, we have 1, 2, 3, 4. 0 from 1, 4. 1, 2, 3. Actually, it's not 4. 0, 2 something has more. 0, 2 has some more. Yeah, 0, 2 has this. Hold on, we are not trying to count how many of them pass. What are you doing? We're just given the current one. We just need to identify whether it passes or not. Right, well, I think I'm doing it wrong. I'm doing like a more extended version of it. No. So basically I'm just saying we can check each value, right? We check the first value. If it's 0, we move on to the second value. If it's 1, we can move on to the next value. So these are like, if it's 2, we move on. And then whenever we encounter a value, right, we just say at a certain position, there's only so many, like at this first position, the only viable is 0 or 1, right? Otherwise, it's going to fail. And then the second position, now depending on whether the first one is 0 or 1, and the second position, if the first one, like how can we code it? Like the second position, if the previous position is 0, and the second position, say like it's 2, oh, then we know what are the values in front of it, right? Because if it satisfies, then we know which value it is. So the first value is either 0 or 1, right? And if it's 0, then we go for the next one, right? And the next one, basically, it's running the same, and then we can just decrement everything by 1, right? We can decrement everything by 1, and then run the same logic. And then if it's 1, then the next value has to be 0, right? There's no other way. If it's 1, and we go to the next one. If it's 1, if the first value is 1, we can actually move 1 further to see if the next value is 0. If the next value is 0, then we can go to the next one, right? And then we go back to the 0 situation. And everybody can decrement. Actually decrement 2, right? Decrement 2. Let's see a 1, 0 situation. 1, 0 situation, and then we go to the next one. That's actually 1, 2, 3, right? 3, and everybody need to decrease by 2. Which in this situation, yes, this is a recursion. This is a recursion. Like if it's 1, I think, yeah, if it's 1, we just check the next one is 0. If it's 0, then we go to the next one, but we can have a decrement, right? We're gonna say is permutation A. No, it has to be a helper. We're gonna def helper. So we can have the index and dec, right? So both are integers. And this will return Boolean value. And of course, we're going to check the index. We're going to say if if a index decrement, right? If a index decrement is larger than 1, then return false. No way. Else, we're gonna say if index decrement is equal to 1 and index plus 1. Ooh, can we even plus 1? So if we cannot plus 1, which means we're already at the end, and that if we go there, that means it's true, right? So basically, what we're gonna say is, if that's the last one, like if index, I like to have n equals ln a. So if index is equal to n minus 1, which is the last one, we can return true. That means we have come to the end. Now it means index is not the last one, so we can do this, and we can do plus 1, right? We can do plus 1 because index is not the last one, and we say it's not equal to 0, right? Then we can say return false. Next situation. Next situation is current is 1, 0, and then we're gonna do two situations. If a index minus dec equals 0, right? Equals 0, then we're gonna return helper index plus 1, dec plus 1. Right? That's we move on to the next one. And if a index, no, it's actually going to be the else. All right, let's not do that. Let's just write it out. All right, and then that also equal to 0. So both equal to 0. Then we're going to return helper index plus 2. Can we do plus 2? Well. Index plus 1, index plus 2. I'm thinking about it. I might not be able to do plus 2. Like, if these are good, right? And then we try to go to the next one. Or if I'm currently at the end, then let me think. And I do index plus 1, right? So I say if it's this, then we say true. And let me do these situations at the end. So these two straightforward, right? And then we say if that's equal to 1, and then we say if okay, hold on. I say one at a time, right? One at a time is a 0. If it's not 0, it will false. If it's 0, we'll go to the next one. Now we have index is 1, right? Which means if it's equal to n or n minus 1, because n minus 1 we have to consider this, and then we can false. Okay, so we can do if this is larger equal to n minus 1, and return true. So if this will return true, and else, right? Else means it's equal to 0, right? Then we're gonna return helper index plus 2. We can do that because this will become n, so it'll be plus equal to 2. when a index plus equal to 2 and dex is also going to plus 2. And that's it, I guess. And this can actually be written in one line. Return if, and this is else this. And then we're going to run return helper 0 and deck. What's the deck? Initial deck is 0. All right, let's try it. We passed some, but we didn't pass all. Okay, I think we have to focus on this. All right, let's see, what was the problem? The problem is, so initial is 0. All right, initial is 0. And I say the first one is 0, return helper, so +1, deck +1, so here. And index is 1, -1 is 0, so that's good. So we go here, deck becomes 2, and then it's 0, that's good. Come here, deck equals 3. So now it becomes 1, all right? And oh, here, this one. Forgot deck. Okay, now we pass. Now we pass everything. All right, let's not print A, because that's going to be too complicated. Let's do another test. Let's do 10. All right. Oh no, this is a stupid idea. 10 is too much. Let's just do 6. Alright, 700. Yep, I think this is right. We got it. A little bit. Oh man, I think I pressed the Control C again. Yeah, we don't. Let's try. Let's see how long it takes. Actually, I don't know how long it takes. How long did it take? That's not too bad. All right, submit again. This one shall be right. Yep, there we go. That is the solution. I mean, these are tail recursions. I can actually write this into a. I'm gonna rewrite it. I think this can be written into a loop. I don't have to do recursion though. So check here. Okay. Let's do solution 1. Recursion solution. The intuition is that if the start of the array is 2 or larger, then we always return false. Right? No question about it. If the start is this, we always return false. This is because there are at least, okay, we have to do, there are 2 intuitions, right? 2 intuitions. First and most important intuition is that we return false if and only if there exists a global inversion that is not a local inversion. Right, that's the first intuition. The second intuition, right? The second intuition is that if the start of the array is 2 or larger, then we always return false. This is because there will be at least one value smaller than the beginning, at least one value at the beginning that is in a global inversion position, right? So that's why two are larger. If the first value is 0, or the first two values are 1 and 0, then we can proceed to check the next or the next value respectively. When we check, we can consider that as a recursion, because we can reduce that value by the number of values already checked, thus turning the problem into a recursive one. For instance, right, given a equals 0, 2, 1, actually 0, 2, 1, right? The first value is 0, which means we can proceed. We're going to proceed to the next value 2. However, since we have already checked one value, we must deduct 1 from 2. Therefore, when we check 2, we are actually looking at 2 minus 1 equals 1, and the next value is that value is 1 minus 1 equals 0. So we are basically checking 1, 0, which is true. So we say 0, 2, 1 is true. The same applies to the 1, 0 situation. It's just that we have to deduct 2 when checking the next value. Alright, so recursion, that's ON, and it runs in 380 milliseconds. Give us a 19% ranking. But since this is a tail recursion, so I think it is possible. It's not possible, it is definitely possible. So iterative. Right, we do iterative. We're gonna eliminate all this. Same solution as solution 1, but iterative. Don't know about this. Alright, how do we do iterative? Index. We start from index. Index I equals 0. While I smaller than n. While I smaller than n. And we say, let's do while true. Easier. If I is equal to nope. And then we're also gonna have a deck as well. Right? Deck is also 0. So we say if no, we're gonna say I is smaller than n, right? And then whatever we do when we exit is going to return true, right? So I'm going to say if ai minus deck is larger than 1, right? I'm going to say return false. And then if ai minus deck is equal to 0, then we're going to say deck plus equal 1, I plus equal 1, and continue. If ai minus deck equals 1, right? Then we say if I plus 1, if I plus 1 equals to n, right? Then we return true. Can we like put this one up there? Yeah, actually we can, right? So if I plus 1 equals n, then we return true. I'll have to return true here. And elsewise, we say, because we need to check return if ai plus 1, right? If ai plus 1 minus deck is not equal to 0, then we return false. Else, then we can do I plus equal to 2, right? I plus equal to 2. Yeah, we have to do this. We can just say if it's smaller than n, then we do all this. And else, we just break, right? Else break. Then if it's smaller than n, and then we check. If it's not, otherwise I plus equal to deck plus equal to. And then when we break, we're going to always return true. Okay, so let's try. This is solution 2. Yeah, this is the iterative version. Direct translation of the first one. I hope this one's faster. I think it should be. Same solution as recursion, but iterative. Just to double check. Always make sure so we don't have any surprises. Okay, are you faster? Please be faster. Slightly faster. Slightly faster. ON is run at 364 milliseconds at a 29%. Okay, pretty satisfied. And then we are going to look at the solution. Oh, no solution. So we're gonna go for problems. And let's see. That's a medium question. Yep, that's a medium question. As expected. Good question. I like it. 775. So I'm gonna record it here. So this one is LeetCode 775. All right, look at discussion. Easy and concise. 3-line. Oh, even easier than mine. Of course, it happens all the time. Okay, all local inversion global. Yes, number of global is equal to number of local inversions. Means all local are local inversions. It also means that we cannot find. Yes, in other words, max AI is smaller than AI plus 2. traverse A and then keep the current biggest number. Then I check the condition. Huh. Okay, so now we cannot find AI larger than AJ. Yes, so in other words, the maximum of the current value up to I is smaller than I plus 2. If not, oh yeah. Then I check condition. Oh, wow. I thought my solution is smart. No, it is not. But we did get it. We did get it, but this is a better one. Much, much better. Yeah. I tried to manage an ideal permutation. Then I found that to place number I could only place I at this of this, so it came to me easier just to check if equals. Then I found that to place the number I could only place that at AI minus 1, AI, or AI plus 1. Well, if I put it here, that's true. If I put it here, yeah, we can have one that's smaller than us. If I put it here, then we will have why? How about we put it even further down? If I put it further down, what's going to happen? If I put it further down, then if I put it further down, what's going to happen? I understand this. This is a good situation. This is a good situation. We're saying like, say 0, we cannot put at the end. Well, that's because of that. Then we have a lot of. Okay, so it's considered not. So this is for itself. This is for itself, and then we put it even further front. Then we have the smaller values would appear on the right side. If we put in here, then we can have all of the small in front, right? So we have I minus 1, number that's smaller than me. And if I am a little bit further down, what's going to happen? What's going to happen is for I plus 1, yes, for I plus 1, if I plus 1 is in this position, then I can be in this position, right? Yes. But if I is in this position, I plus 2 position, then the thing larger than it, right? The thing larger than it. Yes, yes. So, yeah, this means if I put I plus 1 here, then everything in front of it, it could arrange such that this is I plus 1 and everything else is smaller than I. That is a correct one. But if we put in here, I becomes I plus 2, then the allowed values is I plus 1 and all I small, but then we'll have another one that's larger than I. Wow, wow, this is very good. This is very good. This is very, very good. Oh my god, this is beautiful. Beautiful solution. Alright, implement them is not a problem. It's very easy to implement them. Yep, solution 3 from Lee 215. Put a link. Okay, so the idea is The ideal is that but why does this oh yeah, it does work. The ideal is that there exists no pair of AI and AI plus 2 such that it should be like dot dot dot. No such pair of max AI and such that max AI is larger than AI plus 2. Yep. Straightforward, very straightforward. So we just say for I in range len A minus 2, right? Minus 2. And we say max, current max equals 0. And then we say current max equals max, current max, AI. If current max is larger than I plus 2, then we return false. Otherwise, return true. Oh, that's a great solution. Very fast. Okay, so that's that. And then, of course, we have solution 4. I don't have to copy everything. The idea is that for a number I, it can only be placed in positions AI minus 1, AI, and AI plus 1. Reason. Place in AI minus 1. It can only be placed in position in order for in order for the function to return true. Reason. Place in, then the best, then the ideal situation is that the I minus 2 values that are smaller than I is placed to the left of A, is placed in, in A 0 to I minus 2, and the last value that is smaller than I is placed at AI plus 1. No, AI. Right. Place at AI, then the ideal situation is that all of the I minus 1 values that are smaller than I are placed at A 0 I minus 1. Right, third situation, placed at A I plus 1. Then the ideal situation is that all of the I minus 1 values that are smaller than I and the value I plus 1 are are placed at A 0, I minus 1, and the value I plus 1 is placed at AI. Other than these three situations, there will be the function shall return false, right? So coding this is straightforward, which is we're just gonna go, yeah, I think we can return all for I, A, enumerate A. Now we say AI is either equal to I. Oh, hold on. So for I, it has to be, if it's here, then equal 0. If it's here, then the position equal, yeah, so it's the position. It's the position. So it's A minus the position, right? A minus the position is either 1, 0, or minus 1. So let's say this in is minus 1, 0, or 1. And has to be all. And then go 4, and then they all pass. Okay. I'm not going to bother to put these two solutions in so we know that they're good. There's no point. Let's do that. I said it's no point, but it's fun to see how fast they can run. Okay, so that's solution 3. Of course, we're going to remove 3. Try it. And see how it goes. Well, it's much faster. And then this is solution 4. Also try it. It shall be even faster. Oh, probably not. Oh! Wow, this is even faster. Nice. Nice. Alright, we got a 97%. But yeah, so the idea, we almost getting there, right? It's not that bad. It's not that bad, but we can do better. We can do better. Yeah, this idea is very, very smart. One-liner, very, very smart. We identify. That's basically what we're saying, right? We just we use this kind of a bit convoluted way, but we're trying to say the same thing, right? So like, it has to be 0 and 1 in the first position, right? Which is just saying the difference has to be 0, the difference has to be 1. But this is definitely a better way of doing it. All right. Anyway, it's good. We solved it, and we wrote 4 different solutions. Actually 5. But the first one is, it's bad, but it's intentional, like intentionally bad. Anyway, that's it for today. See you guys tomorrow. Adios.